So now what I want to do is I want to look at the homework questions and go over a couple of those. So I'm going to look at problem 23, and let's look at 23A. And the way that's drawn in your textbook, you've got a ring that looks like this, and there's a CH3 down here in the axial position, and there's a chlorine up here in the equatorial position. If you were to number these carbons, you would number them like this. So the name of this compound would be 2-methyl, right? One chloro, because chloro comes first, 2-methyl cyclohexane. And because this methyl group is clearly on the bottom of the ring and this chlorine is clearly on the top of the ring, this is the trans isomer. The first thing I recommend doing when you're looking at flipping the chair and drawing a different conformation is any of the atoms in the ring that actually have substituents on them, I would recommend drawing in the equatorial substituent. So we want the equatorial substituent here on carbon 2, we want that bond to be parallel to the carbon 1, carbon 6 bond. So we're going to show that hydrogen. And then we want to show the equatorial position off carbon 1, and that equatorial bond needs to come out parallel to the carbon 2 to carbon 3 bond. And it needs to point out away from the ring rather than in towards the center of the ring, because that's where that position would be. So now I have the 4 atoms on there. It's always a good idea to show both of those atoms. So I want to draw the ring flipped version of that. So what I'm going to do is I'm going to move carbon 5 down, and I'm going to move carbon 2 up, and I'm going to draw the chair part as the mirror image. So instead of looking like this, where the chair is kind of pointing off to the right, the chair is going to want to point off to the left. So I'm going to draw my chair like this, right? This is carbon 1, this is carbon 2, and I'm going to have an axial position and an equatorial position on carbon 2. This bond should come out parallel to the 3,4 and the 1,6 bond again, and I will have a axial position and an equatorial position off carbon 1. When I flip the chair, sorry, how about now? Can you see it?
Yes.
Okay. Sorry, don't know what happened. I just closed it and reopened the screen, and it apparently is working. So I've got my trans isomer here, right? We've got the methyl group in the axial position pointing down. We've got the chlorine in the axial position pointing up, and I've drawn my hydrogens. The bond from the carbon 2 to the hydrogen needs to be parallel to the 1,6, and the bond from the carbon to the hydrogen here needs to be parallel to the 2,3. When I flip the chair, I'm moving carbon 2 up and carbon 5 down, so I've got the chair part looking like the mirror image, right? You'll notice that if I draw just the chair part without the substituents, there's a mirror plane down here, so the 2 chairs reflect into each other. So I know that this hydrogen that was on carbon 2 was in the equatorial position is going to be pointing up, and I know that this methyl group that was in the axial position will move into the equatorial position. Notice that the hydrogen is on the top of the ring here. It's still on the top of the ring in the other chair. The methyl group is on the bottom of the ring. It's still on the bottom of the ring because this bond is pointing a little bit down. The chlorine that was axial, right, is going to end up equatorial, and the hydrogen that was equatorial is going to end up axial. So whenever I do a chair flip, all of the axial and equatorial substituents interchange with one another. So here's the other chair, right? Both Cl and CH3 are equatorial. Okay. That's more stable than having both Cl and CH3 axial. Right. You'd like to keep as many groups as possible in equatorial positions in order to get a good stable chair. So the original drawing was the most stable. or sorry, this is the least stable, right? So we know that delta G of reaction in going from our reactant to our product delta G of reaction will be negative because we're going to release energy. The amount of energy that it's costing us to put that chlorine in the axial position and costing us to put that methyl group in the axial position, both are going to be relieved. So in the reactant, the methyl in the axial position costs 1.70 kilocalories per mole. And moving it to the equatorial releases, right, that 1.7. So negative 1.70 kilocalories per mole. Because it's releasing, it's exothermic. And then the chlorine in the axial position costs 0.52 kilocalories per mole. Right? So we're going to release, right, a negative 0.52 kilocalories per mole by moving it to equatorial. So if we add together the amount of energy that we're releasing by moving the methyl group and the amount of energy that we're releasing by moving the chlorine, we're going to get negative 2.22 kilocalories per mole. That's not actually the right final answer, though, because if you look at this structure, you'll notice that with the chlorine here and the CH3 there, if I draw a Newman projection looking down that bond, and so I've got my front carbons out like that, and I've got my back carbon coming down like this. So if I'm looking down the C1 to C2 bond, right, carbon 1 is the center here, carbon 2 is the back, there's a chlorine out here in the equatorial position and a hydrogen axial, there's a methyl group in the equatorial position and a hydrogen axial. Over here, everybody's hydrogen. All right, so this is carbon 1, this is carbon 2. The CH3 and the Cl have a 60-degree dihedral. That's a gauche relationship. And I don't know how much energy that costs, right? That's an unknown energy. Let's call it X. So the real difference in energy between the two will be delta G0 is equal to negative 2.22 plus X. The textbook answer key completely ignores that gauche interaction and just says that the answer is minus 2.22 kilocalories per mole, but you really shouldn't ignore that gauche interaction. Does that make sense? How I did that? So you'll find as you go through those that in the cases of A and F and G, the answer key is actually incorrect because I haven't considered all of the possible strains. The other ones, the answer key is correct and everything's just fine. Would it be helpful for me to do another example, or would you like to work on another example yourself? Talk to me. What's the best thing at this point to help you with this? So I can go through another example if you'd like.
Another one.
Another one. That's what I thought you'd say. So let's take a look at G. Right, so this is 23G. And the way that chair is drawn in the textbook, you've got an OCH3 group there, and you've got a CH3 group here. Right. So the first thing I want to do is I want to draw in the other substituent. So that's an equatorial position. You'll notice this bond comes out parallel to the one bond once removed. If I were to number this chair, that's carbon 1, 2, 3, 4, 5, 6. The oxygen takes precedence over the methyl group, so I want the methoxy group to be at carbon 1. Right? So this is 3-methyl, 1-methoxy cyclohexane. So I want to draw in the axial position pointing straight down on carbon 1, and I want to draw in the axial position pointing straight down on carbon 3. So I'm actually seeing all of the substituents on there. Right? It's probably fairly obvious that these two hydrogens are both on the bottom of the ring, which means they are cis. If the two hydrogens are cis to each other, then the methoxy and the methyl must also be cis, right? So the OCH3 and the CH3 are both on the top of the ring, which means that the full name would be cis, 3-methyl, 1-methoxy cyclohexane. So that's my reactant. Because everybody's in an equatorial position, that's going to be the most stable. And when I flip the chair, right now I want to make that chair point the other direction. The methoxy group is now going to be pointing straight up. Oops, that's an OCH3, not a CH3. And the methyl group will also be pointing straight up. Right. So I've got a large group in the axial position here. I've got a large group in the axial position there. That's a lot less stable. So in this case, unlike A, the original drawing was the most stable form. So now we have to see how much energy it's going to cost us to switch from here to there. So delta G of reaction is going to be equal to the amount of energy it costs to put a CH3 axial plus the amount of energy it costs to put the OCH3 axial. So we can look that up in the table. The CH3 axial costs plus 1.70 kilocalories per mole, and the OCH3 axial costs 0.75. And those numbers come from table 4.3, which is in your textbook on page 145. Don't memorize those numbers. I will actually give you that table on the exam, right? There's no reason for you to know those numbers. But the catch with this molecule is this CH3 axial, that cost of 1.7 kilocalories per mole, actually refers to a CH3 group interacting with two hydrogens, right? There are two interactions between CH3 and H, right? Each costing half of that 1.70 kilocalories per mole. So when I'm looking at the actual chair, I have my CH3 group up, I have a hydrogen up, and I have an OCH3 group up. There's actually only one interaction between the CH3 and hydrogen. So that's costing me that half of 1.7, or plus 0.85 kilocalories per mole. And there's actually only one OCH3 versus hydrogen axial interaction. So that costs me half of this 0.75, or plus 0.375 kilocalories per mole. But then there's a really bad interaction between the OCH3 and the CH3 group, right? A very bad 1,3 diaxial between CH3 and OCH3, and I don't know how much that costs. So I know it's going to cost at least plus 0.85 plus 0.375, and I know that this interaction is going to cost me more than the sum of 0.85 plus 0.375, right? But I can't actually tell exactly what the energy cost of moving to that other chair would be, right? The textbook says that it's 2.45 because it just adds these two numbers up and it ignores that more severe interaction between the two large groups pointing axial, but you can't really know, right? So that's another case where the textbook hasn't accounted for all of the possible interactions. Is that helpful? I'm going to save this to make sure that it actually does save, so I don't lose